Chapter 15.4 discusses titration reactions. Titration is the process of gradually adding one solution to another to reach an equivalence point. And you're going to do this in order to discover the concentration of an unknown solution. The titrant is the solution that is being added to the unknown, and that is going to be a standard solution, one that you know the concentration of. So generally that's one that you're mixing up yourself to start with. And the piece of equipment that we're using here that we haven't used before, this is called a burette. This is the clamp, the burette clamp that's used to attach it to your ring stand. So like in this flask here would be the solution that you have that's unknown. You're trying to find the concentration of. So you would have a set volume of that. You would put your indicator in here. Then you're going to put your standard solution in your burette. And again, you would be able to measure the volume off of this. This is more accurate than using a graduated cylinder or a beaker. They're a little bit calibrated a little bit more precisely, and they have this little nozzle on the end that you can open and close so that you can adjust it to exactly the right amount of solution that you need to add until your indicator starts to turn color. The equivalence point is the amount of base added or acid added equals the amount of acid or base originally in the solution. So you're trying to equal them out. There's two ways you can detect an equivalence point. One is with a pH meter, and then the other, which is kind of more common, this is the one that we will use in the lab, is an indicator. The indicator we're going to use is phenolphthalein. So we will know that we have reached the equivalence point when we have a color change, and that is actually the end point of the reaction. So the end point is where you get the color change, and if you choose the correct indicator, your end point and the equivalence point will be the same value. Okay, this is a titration curve, which is just a graph. This one is showing strong acid and a strong base being titrated here. This is the pH value and the amount of base that's being added, and they all have this kind of S shape to them. With a strong acid and a strong base, you expect your equivalence point to be about 7. If you have a weak acid with a strong base, your titration point is going to be slightly above 7. And if you have a strong acid and a weak base, you're going to have your equivalence point at slightly below 7. So depending on what kind of chemicals you're using, you'll choose a different indicator. You need to have an indicator with a transition range that will fall where that equivalence point should lay. A transition range for an indicator is usually about 2 pH units wide, and that's the range that it's going to change color in. With ours, we want to use our phenolphthalein, and we want it to turn light pink, just like this picture here. So real light, almost baby pastel pink. That will tell us that our titration reaction is complete, and we can do our measurements for our volumes and then calculate our unknown concentration. And a couple more drops of our solution to this, and we could get like hot fuchsia. Okay, so we're going to really be careful towards the end of our experiment. Once we start to see that color change occur, that we stop it quickly. The calculation that we're going to use for titrations is M1V1 equals M2V2, or MAVA equals MBVB, where the acid information goes on one side of your equation and the base information goes on the other. So M is molarity in moles per liter, and then volume can be in either liters or milliliters as long as it's the same on both sides. So here's a sample problem. This one says we've got 40 milliliters of HCl, so that's the volume of our acid, of unknown concentration, so that's the one we'll be searching for. That is being titrated with 0.55 molar sodium hydroxide, so there's our base concentration. The volume of the base needed to reach the equivalence point is 24.64 milliliters. So there's the volume of our base. We want to find out the molarity of our acid. So we're going to write out our titration reaction first. Okay, we need to find out the mole ratios. Now for this one, HCl plus NaOH, any titration reaction is going to give us a salt and water. Not just sodium chloride salt. Remember, salt is an ionic compound. This one gives us NaCl, it's just a double displacement, and then the hydrogen combines with hydroxide to make water. Now, this is all 1-to-1 ratio, it's balanced, so we don't have to do anything else with it. I'll show you one that is not a 1-to-1 ratio that you have to do an extra little step for. Then we're going to write out our M1V1 or MAVA equation and plug in our values and solve, and this will allow us to find the concentration of our unknown acid. In this case, it ends up being 0.3388 molar. Now for this one, okay, it says if the titration reaction is not a 1-to-1 ratio, you must compensate with your M1V1 equation. So in this situation, I have barium hydroxide combining with hydrochloric acid to make BaCl2 and H2O. Okay, this is my neutralization reaction. Now to balance this, I have to end up putting a 2 coefficient in front of my HCl and a 2 coefficient in front of my water. Now once it's balanced, I only need to pay attention to the acid and base, not the conjugates. Okay, so when I write my MAVA equation for this particular problem, wherever the coefficient is, I need to multiply the opposite side of the MAVA equation by that. So here I have a 2 coefficient in front of the acid, so I multiply the base side of the equation by that coefficient. If this were a 3, I'd multiply by 3. If it were a 4, I'd multiply by 4. It's whatever the coefficient is. If the coefficient were in front of my base, I would multiply it by the acid side of the equation. So it's always the opposite.